Hello students, today we are going to learn the shielding effect or screening effect. So the topics of this concept regarding shielding effects are concept of shielding effect and effective nuclear charge. We are going to learn first the concept of shielding effect and effective nuclear charge. What is the meaning of effective nuclear charge? Second, factors affecting the magnitude of screening effect. What are the factors important for screening effect? We are going to learn. Third factor is Slater's rules, that is the calculation of shielding constant, and after that we are going to calculate the JEE effective for each element, that means effective nuclear charge. Fourth, variation of screening effect sigma in the periodic table. Fifth, variation of effective nuclear charge in the periodic table. Sixth, application of effective nuclear charge. Seventh, application of shielding effect. And eighth, problems related to shielding effect and effective nuclear charge. Okay, so let's start our lecture today, that is shielding effect. So what is the phenomena of shielding effect? We are going to understand this phenomena in this picture, that the central, we see that this is the central, and in this central of the atom we see there is nucleus, and nucleus contains protons and neutrons, and protons are effective to bound the shells. These protons have sufficient power, the positive power, positive charge. Protons are generally positive charge, which has sufficient power to attract the shells, and the shells contains electrons which are negatively charged. So electrons are attracted towards nucleus, and in this way first shell is K shell, second shell is L shell, and that is formed. So what we see, that the valence shell electrons are guarded by the inner core shells electrons. So here inner core shell is K shell. K shell electrons, these two electrons guard the L shell electrons. So these inner core electrons make some repulsive force toward the outermost shell electrons. So these type of repulsive force generated by inner core electrons towards the valence shell electrons from the nucleus, it is called the shielding effect. It is called the shielding effect. So inner core electrons make some repulsive force towards the valence shell electrons. There are two types of force. One is attractive force, because of nucleus the protons are attracting each shell's electrons towards itself, so the atom is very much stable. And another force is generated due to repulsive force. This kind of repulsive force generated by inner core electrons towards the valence shell electrons. So this is the shielding effect, and in this way the attractive force of nucleus becomes reduced, somehow reduced due to this repulsive force. The effect of nuclear charge become reduced. So Z becomes reduced due to this shielding effect. So how much nuclear charge get reduced, we need to calculate. So this is the JEE star, that means JEE effective. It is called JEE effective, that actual nuclear charge, that is JEE, that is the actual nuclear charge. And we need to subtract some of the repulsive force generated value, and that repulsive force generated value is called shielding constant, that is sigma. This is shielding constant. So this shielding constant, the factors affecting the shielding constant, generally the factors, what are the factors? The factors are inner core electrons, and also the shape of the orbitals, in which the electrons are situated. If it is s orbital, then it will shield the nucleus more than p orbitals. In this way the shape of orbitals can determine the shielding effect. Shape of orbitals or orientation of orbitals. So the shielding effect of s orbital greater than p orbital, and p orbital greater than d orbital, and d orbital greater than f orbital. So in this way shielding effect decreases. So these are the factors which are governing factor towards shielding effect. Now we need to know the shielding constant. So how we can calculate the shielding constant sigma? And it is calculated by Slater's rule. And what are the rules? We need to understand the rules. So now Slater's rule, that is the calculation of sigma, governed by some rules. So first rules, electronic configuration of elements can be written as follows. So we can group the orbitals in this way, that one group is 1s, next 2s 2p, another group 3s 3p, another group 3d, separate group 4s 4p, another group 4d 4f, another group 5s 5p, and so on. So in this way we can group together the orbitals. In this way we can write this. Second point is contribution of screening constant for the following groups are as follows. So each groups, in these groups, the electrons are situated, and each electron contribute different value of shielding constant to the shielding constant. So different value to the shielding constant means, so here ns np electrons, if there are 5 electrons, so 1 electrons being shielded by 4 electrons in the same orbital, 3s 3p orbitals. So the 4 orbitals can contribute to the shielding constant of the value 0.35 each, because we see ns np group electrons contribute 0.35 each. So same orbital ns np group contributes 0.35 each, except 1s group, that is 1s group, it is in this way electrons contribute 0.30 each. And n minus nth shell, that means it is the third shell 3s 3p, n minus 1 nth shell, that means 2s 2p shell, the electrons contribute 0.85 each, and n minus 2 shell and so on, the electrons contribute 1.00, that means 1 each to the shielding constant. So this is for ns np orbitals electrons. And next point is for d or f electrons, and in this case df electrons, the nd nf shell contribute 0.35 each, and n minus 1, n minus 2, all electrons lying left to the nd nf contribute 1.00 each. And third point is electrons to the right of the ns-np or nd-nf groups are not effective in shielding the ns-np or nd-nf electrons. That means, so here if the valence shell is 3s 3p, after 3s 3p there is no electrons, 3d 4s 4p, there are no electrons. So these orbitals cannot contribute any value to the shielding constant. The value only left hand side electrons or same orbital electrons, except one electron. One electron is guarded by other electrons. So 3s 3p, if there is 4 electrons, so 1 electrons we need to guard by 3 other electrons, and remaining 2s 2p electrons shield the valence electron, that 1 electron, and also 1s electron can shield the valence electrons in this way. So left hand side electrons can contribute to the shielding constant. So in a nutshell, we can say that the electrons situated left hand side to that of valence electrons that can only contribute to the shielding constant. But the orbitals where no electrons are present to that of valence shell, the left hand side orbitals of that valence shell, that orbitals cannot contribute to the shielding constant. So this is the form, this is the value we need to understand, we need to memorize these things. And to evaluate the shielding constant for lithium, that is 1.7, we see that lithium 1.7, beryllium 2.05, and boron 2.40, carbon 2.75, nitrogen 3.10, and oxygen 3.45, fluorine 3.80, and neon 4.15. By calculating this sigma, I am going to calculate it very soon in this lecture. Just I am going to explain the things, what are the changes are going on due to this shielding effect. So we see that lithium, we see the JEE lithium total effective nuclear charge. Total nuclear charge is 3 due to the 3 protons, beryllium 4, boron 5, carbon 6, and so on. But sigma for lithium 1.7. So effective nuclear charge, that is JEE minus sigma, that is 1.3, and beryllium 1.95. So if we move along the period from left to right, what we see that sigma 1.7, 2.05 for beryllium, and boron 2.40, and it will increase. It will increase when we go from left to right. And when we see that for the case of JEE effective, what we see, JEE effective also is going to be increased, that 1.3 becomes 1.95, next one 2.60, next 3.25, and for nitrogen 3.90. Again we see for oxygen 4.55, for fluorine effective nuclear charge 5.20, for neon 5.85. So effective nuclear charge increases while moving from left to right along the period. So if effective nuclear charge increases, then what happens? The atomic size, the valence shell becomes shrinking towards the nucleus. The atomic size become reduced, and for this reduced atomic size, what happens? What happens? The ionization energy become increases. So electronegativity of that atom increases, electron affinity of that atom increases. So while we're moving from left to right, these kind of changes happen during the moving from left to right. We see that in these elements, ionization energy, electronegativity, electron affinity, all those things, oxidizing properties, all those things are increased. So this is the from metal to non-metal. While moving from left to right, we are going from metal to non-metal, because lithium, beryllium, these are metallic in the metallic groups. And while we're moving from left to right, we see that oxygen, fluorine, these are non-metals. Now, if we move from top to bottom down the group, what we see that lithium, sodium, potassium, rubidium, cesium. The J for lithium, actual nuclear charge 3, sodium 11, potassium 19, rubidium 37, cesium 55. And what happens to the sigma? The contribution for lithium, sigma 1.7, sodium 8.8, potassium 16.8, rubidium 34.8, and cesium 52.8. And what is the J effective for these elements? Lithium 1.3, sodium 2.2, potassium 2.2, rubidium 2.2, and cesium 2.2. But we see that almost the J effective is similar, same throughout the transition down the group. The J effective is going to be same, but the sigma increases. Sigma increases, shell size increases, sigma increases, but J effective remains same. So what happens? Atomic size increases. So due to the lack of increase nuclear charge, effective nuclear charge is not going to be increased so much, the atomic size become increases. So the combined effect of shielding effect and shell size and nuclear charge helps us to determine the atomic size down the group increases. So in this way, periodic table we can understand. So now I am going to calculate the potassium sigma. How can we calculate the sigma for potassium atom? So first, potassium, what we see that potassium for atomic number 19. So the configuration is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. This is the potassium 19 electrons situated in each orbitals, and last valential orbital 4s and nsnp. So for 4s electron, there is one electron, so we cannot count this electron, because this electron is the last electron, and this electron situated in the valence shell, and these electron is shielded by the inner core electrons. So we calculate the sigma for 3s 3p. That means if nsnp contributes 0.35 for each electron, but n minus 1 from the valence shell, if we move left hand side, n minus 1th shell contribute 0.85. so 2 plus 6 electrons are present in third shell, so 8 into 0.85 plus 2 plus 2 plus 6, so remaining all electrons contribute 1, so 10 electrons contribute 1.00 to the sigma. So how much the values? 10 plus 0.85 into 8, 6.8. so that is 16.8 is the sigma value. And what will be the Z effective value? Z effective, actual Z, that is Z minus sigma. Actual nuclear charge is the number of protons, that is 19 minus 16.8, and that is equals to 0.217, 18, 19. So 2.2, that is the Z effective value, and it is reported in the literature also. So potassium for that is Z effective 2.2, it is reported also. So in this way we can calculate the shielding constant and the Z effective. So this is the way we can understand the shielding effect. So what are the problems regarding JEE and NEET examinations? So here we see that calculate the effective nuclear charge experienced by the 4s electron in potassium atom, which is already done in this lecture. And you are going to calculate 3p electrons in chlorine atom, 4s electron in zinc atom, 3d electron in zinc atom. In this way you can solve these kind of problems many times in JEE. The examiner asked this kind of questions also. And the application of shielding effects. So now we are going to understand the application of shielding effect. Application. So what are the application of shielding effects? So first one, we are going to understand the atomic size trend. Atomic size trend in the periodic table. Atomic size trend in the periodic table. In some cases there is some anomalous behavior of the periodic table, because we know the ionization energy value, ionization energy trend. We can explain ionization energy trend for some anomalous behavior, that is beryllium and boron, magnesium and aluminium, and so on. So beryllium, boron. So our understanding that the ionization energy will increase if we move from left to right. So our expectation is boron ionization energy, fast ionization energy, will be higher than beryllium. But in actual case, in actual scenario, ionization energy trend, actually we see beryllium greater than boron and magnesium greater than aluminium. So why? Because beryllium, if we see that beryllium electronic configuration, that is 1s2 2s2, because beryllium 4 atomic number, and boron 1s2 2s2 2p1. And here what we see that the last valential electron for beryllium is 2s. The s orbital is very much spherically symmetrical, and it can cover the nucleus in good manner, spherically symmetrical ways, so good manner. But for the case of boron, we see the valence electron situated in 2p orbital, and 2p orbital is not symmetrical. 2p orbital, the shape of the 2p orbital is like dumbbell shape. So here we see that for the 2p orbital it is not good for shielding, but for the case of 2s it is very much good, effectively shield the 2p, effectively shield the 2p orbital, effectively shield. So for 2s orbital, guard the 2p orbital effectively. For the case of beryllium, what we see, the 2s electron itself, the 1 electrons, the same shell electrons are less effective to shield, and 1s electron shield. So here what we see that 2s electron and 1s electrons, they are inner core electrons, and which are very good providing the shielding effect. And that's why the 2p electron from the nuclear charge, 2p electron, the effective nuclear charge becomes decreases because due to the effective shielding, the 2p electrons experience lesser effective nuclear charge. But for beryllium, the effective nuclear charge for 2s electron is going to be higher than in the case of boron. This is the similar reason why magnesium ionization energy is greater than aluminium. So this is the beautiful understanding for periodic trends with the help of shielding constant. Now third point is we can understand that inert pair effect, and I am going to make another video regarding inert pair effect. Just we need to learn about this term, inert pair effect, and also we can understand the lanthanides and actinides, contraction. I'm also going to make a separate video lecture with lanthanides and actinides contraction. So this is the beautiful application of shielding effect. And what is the importance? We know that the periodic table trend, atomic size trend, ionization energy trend with the help of shielding effect. Now shielding effect connected to the Z effective, so we are going to understand the application of Z effective also, effective nuclear charge, because the shielding effect connects Z effective nuclear charge with the equation that Z effective equals to Z minus shielding constant. So we need to just learn that what are the application of effective nuclear charge. So the application of effective nuclear charge helps to understand the trend in ionization energy trend for elements. Again, the ionization energy trend, the first ionization energy less than ionization energy, second ionization energy less than ionization energy, third ionization energy. So successive ionization energy trend we can understand with the help of effective nuclear charge. And next we can understand the atomic size, the radius of cation C cation always less than the radius of parent atom. We can understand these. We can understand this radius of anion always greater than radius of parent atom. Also we can understand that why the 4s electron will feel fast than 3D electrons. While filling the electrons, why 4s electron will feel fast than 3D electrons, that can also be understood with the help of effective nuclear charge and shielding constant. If we calculate the value of shielding constant, we can understand that for 4s electron the effective nuclear charge is going to be more. So that's why the 4s electron will fill fast. Then we need to fill the 3D electrons. Next we can understand why 4s electrons are removed fast from transition metal atom to become di-positive. So if we see that for the case of vanadium to vanadium 2 plus or iron to iron 2 plus, so we see that the 4s electron will remove fast. In the previous case what we see that 4s electron will fill fast, but for the second case we see that for the formation of cation the 4s electron will remove fast. And if we calculate the Z effective, then we can realize that it is okay. We understand with the help of numerical calculation also by the Slater's rule. So this is the all about the shielding effect. I hope you enjoy this video and you learn this video, and if there is any problem you can comment. I will definitely rectify those things, those mistakes. And thank you for watching. Also I am going to share that in these days my health is not well, so that's why there is some delay to post these kind of videos. Thank you for watching. Be patient and focus on your learning. Best wishes. Thank you.